All right. So that's the mathematical universe and operations and operators. So this is a semantic picture of the mathematical world. And to operate uh, with these semantics, that's what abstraction algebra is for. So uh, abstractions are really just names. And so a signature is a collection of names. And these names are called abstractions. And each such name is associated in the signature with a shape. Okay? And so we've seen a universe together with a collection of operators is called an abstraction algebra. And now if we put a signature together with an abstraction algebra so that a name of a certain shape in the signature is mapped to some operator in the abstraction algebra of the same shape, then what we get is an abstraction algebra of that signature. And so I'm not really distinguishing between, like, abstraction algebras with signature or without. I mean, they all kind of have some signature, right? So I will just all call them algebras from now on. All right. So here's an example. A calculator again as an algebra with a certain signature, and the signature is given here: 0, 1, at, sub, mal, diff, sum, prot, and iter. And so some of these names are different from the abstraction algebra that we have previously seen. Some are the same. Doesn't really matter because we have the mapping, and all the mapping cares about is really that the shapes are mapped properly. And yeah. And so abstraction algebra also is really a formal language for algebras. Okay, so we have terms and we have templates, and terms evaluate or correspond really to values in the algebra, and templates correspond to operations on the universe of the algebra. And so we have three constructors, two for terms and one for templates. And a term is either a variable application of a variable x to some terms, t, or it's an abstraction application of a certain abstraction from the signature, and together with n argument templates. And a template is just a term where we bind a number of variables, and these numbers and these variables must all be distinct from each other. Okay, so here we know that the abstraction has a certain shape, and the template at a certain position here must correspond to the arity that the abstraction has in its shape at that position. So T1 must have arity M1 and so on, and Tn must have arity Mn. All right. So, and just to emphasize how simple this formal language is, there are just these three constructors. They're very simple. Variable applied to terms, abstraction applied to templates, and a term where we bind variables forms a template. And that's it. So in our calculator example, this is a signature that we've talked about before. And here are now some example terms that we can form with respect to that signature. 0, for example, just a variable x, at x1, divide 1 by 0, divide 1 by the variable x. Here it's apply x to x and 1. And this example here shows that it's really important with which arity a variable occurs. So here we have an occurrence of x with arity 2. It's applied to two arguments. and here is an occurrence of x, and it's applied to no argument at all, so here it occurs with arity 0, and these two occurrences really have nothing to do with each other. Okay, this could be just as well x and y here. That would really not change anything in the meaning of the term. Yeah, so when we talk about variables, about free variables like this, it's always a name together with an arity. That's important. Here we have a term, and this term has as one of its arguments a template, the template I dot mal ii, and so on. And here we have some more complicated examples. The iter abstraction takes actually two proper operations as arguments, and so it has two templates. This one has arity 2, this one has arity 1. And yeah. And so now that we have terms, we can introduce the shapes of abstractions in an easier way than, or maybe in a more convenient way than giving raw shapes. In a theorem proving system, working with shapes is maybe a little bit strange, and we don't have to. We can just write down terms, I call them heads, that have a certain form, and from these forms we can immediately read off what the shape of the abstraction in question is. So, for example, you can see multiplication has shape 0, 0 because it takes just two values as arguments. We can see that sum must have shape 0, 0, 1, and we can see that iter must have shape 0, 0, 0, 2, and 1. Okay, so I've said that terms correspond to values, and templates correspond to operations. And well, this correspondence is evaluation, right? When we evaluate a term, then we get a value, and when we evaluate a template, then we get an operation. And in order to evaluate a term, we need to provide values for the free variables that appear in a term or in a template. And for this, we use valuations. So a valuation on the universe is a mapping that assigns to each combination of a variable and arity n, an operation of the appropriate arity on the mathematical universe. Okay, and so we have just three cases. We have the case of a template, and we have the case of variable and abstraction application. And so when we define evaluation of templates, we just need to consider these three cases. Okay, so when we form, when we do the evaluation of a template, what we do is, it's an n-array template, so that means we take, the operation will take n arguments, and evaluation is always with respect to evaluation, and what we do is, for each combination of arguments, we update the valuation, and this yields a new valuation, and we evaluate the body of the template with this new valuation. And that's then the value that the operation will have for this combination of arguments. We define this recursively, and so the variable application, then we evaluate a variable application by looking up, okay, what is the operation that the valuation associates with this variable and arity pair, and then we recursively evaluate the arguments of the variable application, and we apply the operation to these evaluated arguments. And the same for the abstraction application. We check what operator does the abstraction correspond to in our abstraction algebra, in which we evaluate the abstraction application. And we take this operator, we evaluate the templates that are the arguments of the abstraction, and then we apply the operator to the operations that are the result of evaluating the templates. And so an n-ary template evaluates to an n-ary operation, and a special case of this is that a term evaluates to a value. All right, so now we come to a very interesting topic, alpha equivalence. And what's so interesting about this in abstraction algebra is that the simplest and the nicest way to define alpha equivalence is purely semantic. So we say that two templates of the same signature, they are called alpha equivalent if they have the same arity, and if for all algebras A and all valuations on the universe of these algebras, we have that the two templates evaluate to the same valuation. Okay, evaluate to the same operation. So that's a really nice and short definition of alpha equivalence. Okay, but it doesn't tell us anything about how do we compute actually for two templates, if they are alpha equivalent or not. And for this, we use a common device, de Bruijn terms. And so in abstraction algebra, de Bruijn terms, so the idea of de Bruijn terms is that instead of bound variables, you have these indices which refer to bound variables. And so de Bruijn terms now are made up of de Bruijn indices and variable application and abstraction application again. So note that we have again here just three cases. And this time we don't have any case for templates. That case has been replaced by the case for de Bruijn indices. So there are no de Bruijn templates, there are only de Bruijn terms. And we can see in these examples where we convert templates to de Bruijn terms, why that is. So we see that, for example, the template ij with mal ij, that has two bound variables, is converted to this de Bruijn term here, mal 0, 1, and the index 0 corresponds to the I, and the index 1 corresponds to the j. And but there is nothing that corresponds actually to the binding here, right? This is just a term now. Actually, here's another example where we have a bound variable k that doesn't actually appear in the body of the template, and we can see that the conversion yields the same de Bruijn term as here. So we cannot really distinguish the origin where these de Bruijn terms came from if we don't know the arity. We only know here that, okay, these de Bruijn terms must come from templates that have arity at least 2. But it could be arity 3, it could be arity 4, it could be 5, it could be anything really, greater or equal to 2. Yeah, and here are some other examples. This is just standard stuff. There is nothing surprising here in abstraction algebra to how de Bruijn indices are usually used. Maybe a surprising thing is that we still have free variables appearing here. Only the bound variables are replaced by de Bruijn indices. And yeah, so, but that's also something that appears often in implementations, of course, of theorem proving assistance. our case here is interesting in that we're not avoiding these dangling indices, 0 and 1. They are a natural part. They are natural for us because they arise when we convert templates. All right, so then there's lots of technical work on top of that. It's about 50 pages in the book. As I said, it's at abstractionlogic.com. If you're interested, check it out there. So what does this technical work consist of? Well, now that we have De Bruijn terms, we need to define also what does it mean to evaluate De Bruijn terms. Then we can show that if we evaluate a template, we could just as well convert it to a De Bruijn term and then evaluate the De Bruijn term. That's the same, and that's what we would expect, of course. And then we can define substitution on De Bruijn terms and on the De Bruijn representation in general. Then we have to talk about various properties of compositions of substitutions and so on. And I will talk a little bit about this on the next few slides. But so what's important here is it's a lot of work, but it is straightforward. There are no real surprises, and it's actually nice that everything unfolds so smoothly and pleasantly. So about substitution. Substitution is just a partial function, a sigma, that maps variable arity pairs to a template of the corresponding arity. So variable with arity n is mapped to a template of arity n. And so we write like this, t, and we apply a substitution sigma to this template t. This can be defined what this means for De Bruijn terms. And once we have that, we can play it back to what it means for normal templates. Yeah, so this is also not difficult. And so then the connection between substitution and evaluation is especially clear in abstraction algebra. So if we have a valuation and we have a substitution, then we have a valuation that's induced by the transformation of this valuation through this substitution. And it goes like this. For each variable arity pair xn, if xn is in the domain of the substitution, then we apply the substitution, and then we evaluate what we get with the original valuation. And otherwise, if it's not in the domain, then we just apply directly the valuation. And so we get a new valuation through this. And now the nice relationship we get is if we evaluate a template where we have applied a substitution to, if we evaluate this with the valuation new, then we could just as well just evaluate the template directly with a different valuation, this valuation induced by the transformation of new through this substitution. And yeah, very nice and easy relationship here between substitution and evaluation. And well, after all of this technical work, we arrive at a very simple and intuitive result. And this result connects the semantic characterization of alpha equivalence with its syntactic equivalent. And so the theorem then is two templates S and T are alpha equivalent if and only if they have the same arity, and if the alpha conversion of S is the same as the alpha conversion of T. Okay, And well, alpha conversions are easy to compute, and that means that alpha equivalence is easy to compute as well. And so how do we prove this? Well, we said before, we can see that evaluating a term or its alpha conversion is really the same. So that means if we have two templates where the alpha conversion is the same, then it will also be the case that they're alpha equivalent. And on the other hand, if we have two alpha equivalent terms, what we can do for the signature is we can construct a De Bruijn abstraction algebra for the signature. And this De Bruijn abstraction algebra, that's what I call it, it consists of De Bruijn terms. And so the construction is in the book. And the only thing really that's interesting about it is that this abstraction algebra has a valuation which is the same as alpha conversion. Okay, and so that means if we have two templates now that are alpha equivalent, they must be the same, they must evaluate the same under all valuations, in particular under this valuation that is alpha conversion, and that means that the alpha conversion of those templates must be the same.